So hi everyone, welcome to our third Landscape Live seminar. Today we have Allison Pfeiffer. Super excited to welcome her here. I'm a big fan of hers, so I'm really excited personally. Allison is currently an assistant professor in the geology department of Western Washington University. And before that, she was at the University of California, Santa Cruz. And she's going to be talking to us about some American rivers today. So I'll pass over to Allison and share your screen.
Wonderful. All right, well, good morning or good evening to all of you, depending on where you are. Thank you for the introduction, Rebecca, and the invitation to be here. So in the next hour or so, I want to take some time to consider channel response sort of within a single region. And I'll argue that thinking about this within a region is sort of a powerful or helpful way for us to consider this problem. Oh, there we go. So the work I'll talk about today has been a collaboration with all of these folks, and especially Brian Collins at the University of Washington, where I did my postdoc. And this, the inspiration for this project came out of a desire to better understand flooding hazards in the Pacific Northwest. So the frequency of flooding can change through time for two different reasons. The first is a change to hydrology. So here we have peak annual discharge for a number of decades at the Nisqually River National, and we see that the intensity of flooding is increasing through time. So non-stationary hydrology, I think, is the first example of changes in flood hazards that many of us think of. The other way, though, there's another flavor of changes to flood hazards, and those are geomorphic changes. So river channels can in size, widen, and or decrease in roughness, which would result in more capacity for water and therefore floods that occur at a higher discharge than they did in the past. In contrast, if we have channel narrowing, aggradation, or increases in hydraulic roughness, floods will then occur at lower discharges than they did in the past. So this is inspired by one of Louise Slater's studies a couple of years ago. So they looked at these trends in the geomorphic component of flood hazards for 400 long-term United States Geologic Survey stream gauge sites. And they found that, some of these sites were showing a change in the flood hazard frequency that was an increase in the flood hazard frequency, others a decrease due to this channel capacity. And if we blur our eyes, perhaps we can convince ourselves that there are some regional patterns here, although certainly in plenty of regions, there's a lot of variability. And there are two things that this work brings up for me. The first is that, okay, these are shifts in response to environmental signals, but what environmental signals? The channel capacity can change through time due to changes in either the sediment supply or the hydrology. So sort of what signals are driving this? And the second thing is that in this work, they were just measuring the linear trends. And since then, they've looked at sort of oscillations with climate patterns. But what if there are changes through time that aren't tied so distinctly to climate oscillations? And so we're gonna think about the patterns beyond just linear trends or cyclic patterns. So we're going to take a moment to make sure that all of us are geographically oriented. So we're in the Pacific Northwest of North America here, and I am currently in Bellingham, marked with this little star, just south of the forbidden Canadian border at the moment, and on the homeland of the Nooksack and Lummi Coast Salish people. So we're on a convergent boundary with two notable mountain ranges, the Olympics, which are glaciated, and then the much larger Cascade Range, which is glaciated and has a smattering of stratovolcanoes, some of which are popping out here with their snow-capped peaks. So at the last glacial maximum, the Cordilleran ice sheet came south and into the Puget Sound lowland, which separates these two mountain ranges, and deposited sort of large packages of unconsolidated sediment in much of the lowlands around here. Okay, so the goal in the next hour or so is to quantify recent channel change in this region. And by recent, I mean engineering timescales, decades to centuries. And by in the region, I mean that I think, as I said earlier, that channel change is a function of sediment supply, at least in part. And the delivery, the magnitude and the pattern of the delivery of that sediment matter a lot to how frequently and the magnitude with which the channel changes. And so I think taking a regional perspective is sort of enlightening here. So before we get into the data, I want to take a moment to consider a few case studies, some of which you all might be familiar with and some maybe not. So let's begin with the Toutle River. So this is a photo of the North Fork Toutle River in May 1980, right after the eruption of Mount St. Helens. And this certainly affected the river channels in this area. So this is a repeat study site that is sort of in that area of that photo I showed you. And in response to this major instantaneous disturbance, there was aggradation of more than 100 meters. And in the, say, 2 to 4 years after the eruption, the channel incised 20 meters and has since stabilized. Okay, so we'll turn now for another sort of quick tour case study to the next volcano to the north. So in the mid and late 2000s, there were a series of very large floods and debris flows in the Nisqually River and especially down to Tahoma Creek here. And during this time, there were some reaches of river downstream that widened their active channel substantially and others that narrowed during the same time. And this has been connected to proglacial debris flows that were, to be clear, these are eroding the mountain edifice and then redistributing that sediment downstream, which then gets reworked especially by these sort of blowout storms. So we'll move away from volcanoes for just a moment and go to the Skokomish River. The Skokomish has been rather problematic in recent decades. So it's seen a threefold loss in channel capacity due to both aggradation and narrowing. And this sort of downstream channel change has been attributed to a combination of naturally high supply of coarse sediment in the South Fork. So the collapse of these paraglacial bluffs, all of this is gravel-sized material. And combining that with dam operations that have decreased flow coming out of the North Fork. As a last stop on our case study tour in this area, I want to consider the Nooksack River. This is right in my sort of backyard here. And Scott Anderson and Chris Conrad have connected USGS gauge data in this area to show that in the North Fork, there was aggradation and then incision that happened. And if we trace the channel change at these lower gauge sites, we see in later decades, aggradation and incision happening sequentially at each one. And they call this a downstream propagating wave of aggradation. And the numbers sort of work out where the timing is actually pretty feasible for this being sort of a sediment transport wave. And they connect the upstream aggradation to a time period of wet climate and the incision to a time period of dry climate. So this is sort of giving us, I think, a helpful view into perhaps how climate gets recorded in channel change, or can, in this area. Okay, so our goal today was to consider regional patterns in channel change. And I think that when I think about channel change in this area, I think about the case studies. And for many of you, you might have sort of your particular favorite landscapes that you study a lot. And you maybe have the sort of case studies of channel change that you think about as well. But I think these case studies potentially bias us towards the excitement, right? Towards the exciting places. And so I want to take a broader and admittedly much coarser view of this problem. But before we talk about channel change, I think we should consider gravel mobility. Gravel mobility is the process by which these alluvial rivers change their geometry. And so this work comes out of my PhD, got published a couple of years ago now. And we're going to compare the bed mobility between regions in the US. The US because the stream gauge records are really good and easy to access. And the West Coast sites that I'll be talking about, these sites have high sediment supply to them, and they're subject to many storms that are about a day in duration throughout the winter. And across the West Coast, these very often come as rainfall associated with atmospheric rivers or synoptic storms coming off of the Pacific. In the Rocky Mountains, these sites are all high Rocky Mountain and sort of medium to low sediment supply with snowmelt dominated floods in the sort of spring and early summer. The Appalachian sites have low sediment supply and very weak seasonality to the high flow events across the sort of East Coast or Northeast. And we're going to do this using these USGS multi-decadal discharge records using the 15-minute data, which is especially important when we're looking at these areas that have really brief duration peak flows. And of course, an approach like this requires that we make a lot of simplifications. I think the most egregious of which is that here we're going to assume that the discharge to flow depth scaling and the grain size don't change through time at any of these sites. And I recognize that they probably do, right? And that probably does matter. But I think we can learn from this exercise nonetheless, having acknowledged that simplification. So here's quickly a sort of overview of the data processing time or pipeline that we have. So we're taking the discharge stage rating curve and this set of field data that are available for each site. So stage, discharge, flow depth, and flow width available for every point in time when there was a field measurement. And from those, we can create a discharge depth rating curve, because of course depth and stage are not the same, and a discharge width rating curve. Plug those into the time series of discharge, get out a time series of depth and width, use that along with channel slope to estimate bed surface shear stress for every 15 minutes for the decades of record. Combine that time series of bed surface shear stress with a measured grain size distribution for each one of these sites, plug them into a sediment transport model, and calculate the riverbed mobility. Okay, the sediment transport models we can use have all sorts of different configurations to them. And I'll just tell you that regardless of the model that I use, the region to region patterns persist. But what I'll show you today is using the Parker 1990 model with a slope-dependent critical shield stress. Okay, so here is just sort of a snip of the results. So here I'm showing you data from one river in each of the regions and just for 3 years of time. On the vertical axis is average flow depth, and I've colored the curve by the riverbed mobility. So an immobile bed up to the threshold for gravel motion is in gray. what we're calling partial mobility. So from the threshold to motion to about 2 times the threshold for motion is partial, and then full mobility. Above 2 times the critical shield stress, you tend to have grains all across the bed in motion. And so that's in dark blue. So in the Appalachian site, we see that weak seasonality to the high flow events and that they are very brief in duration. At this particular site, the bed begins to mobilize above bank full flow. I could have just as easily found an Appalachian site that has mobilization below bank full flow. The Appalachian sites vary substantially in this regard. In the Rocky Mountain site, we see those lovely late spring high flow seasons popping out in the data. And I think notably here, the riverbed mobilizes just below the bank full flow depth, which fits beautifully with the sort of bank full threshold channel story that we often tell about how alluvial rivers work in our textbooks and courses. And then we have the West Coast site, which we see those many events throughout the wet season, and we see the much higher mobility here. So the transition to a partially mobile bed happens in almost every one of the peak flow events during high flow season. And then in this river, the transition to full mobility happens around bank full flow. All right, I want to emphasize that what I'm showing you here is not just a hydrograph, right? So the timing of the peak flow events is what is determining the shape of that curve, that in the channel geometry. But it's really the geomorphology, the relationship between channel geometry and bed surface grain size that's determining where along that curve the mobility transitions occur. So a coarser grained channel of the same geometry and hydrologic forcing might have a transition that's up higher here. All right, so here's a little bit more of the data. What I'm showing you here is 3 different rivers from each of the 3 regions. And I've stacked the years on top of one another. So we're going from the mid 80s, 90s to 2017 and colored using those that same color scale and through the water year from left to right. So what I hope you see here is that there are differences between rivers, but that the regional sort of climate and sediment supply, as reflected in the bed surface grain size, pulls out these differences in the character of the different regions. And in particular, thinking about the West Coast, through the lens of channel change, this suggests that we have many opportunities to remake the channel geometry, to a grade or in size to widen and narrow in almost every year. So the high sediment supply in this region gives us ample building materials. It gives us the material required to grade a channel. And these rainfall dominated peak flows that happen in reasonably quick succession, that gives us ample opportunities for construction. So on to part 2. That was the stage is set. So what have the rivers done? So we are going to be looking at 49 long-term USGS stream gauge sites. I've chosen these sites because they have minimal regulation of flow or sediment in the upstream basin, so no large dams. And these are levee-free reaches. And that means that we have been largely kept out of the lowland, which is heavily populated and has all sorts of modifications to the rivers or sort of confinements. So to quantify channel change for all of these rivers, we're going to use specific gauge analysis, which is otherwise known as stage residual analysis. So this approach exploits repeat channel measurements that have been made at stream gauge sites. And so this approach yields a long-term and high temporal resolution record of channel change. And we can compare that to some of the other ways that folks commonly sort of record channel change in for a river. So one common approach is to use historic air photos. So these photos give us a much lower temporal resolution than the method I'm going to show. You know, maybe a photo every 10 years for many sites. And but the benefit to air photos is that you get lateral change for whole reaches of river, not just a single cross section. And another common approach is repeat cross sections. So repeat cross sections also have low temporal resolution to them whenever you can get out in the field. But they give you both lateral and vertical change, so sort of the details of the channel geometry. But again, they are just at a cross section. So I guess I'm saying this because there are benefits to all of these approaches to quantifying channel change. And when we look at this specific gauge analysis, you know, yes, it's just a cross section, and yes, it's just a rough measure of vertical change through time, which I'll argue in a moment. But the high temporal resolution, I think, is an incredibly powerful way to augment some of these more traditional approaches. Okay, so a thing to note here is that these USGS gauge sites are specifically chosen to be laterally stable. There's no reason to put your gauge at a spot where it's likely to get swept away through channel migration. And so this helps us to isolate just the vertical dimension of channel change. Okay, so specific gauge analysis is by no means a new tool. G.K. Gilbert did some version of this when looking at the response of Central Valley of California streams to hydraulic mining. But it has been made increasingly easy with the increased computing power and the availability of data on the online servers. So what we're doing here is exploiting the fact that hydrologic technicians for the USGS go out and make repeat measurements of gauge height and discharge to keep these rating curves updated for each one of the gauges. And these field measurements that they make are, you know, back in the day, they were kept in these tables, and many of these field data have been digitized and put online. But some are still back in the filing cabinet. So what I'm going to show you is mostly data scraping off of the servers, but then we went back and scanned and digitized a whole bunch more of these historical records, like this lovely one from 1941, to sort of extend back the record for as many of these sites as we could. All right. So to get a sense of the channel change through time, we're going to be using stage residuals. And we'll take each one of these dots as a field measurement. The curve is the current rating curve for this site. We're going to throw out the upper half of the discharge measurements. And that's because there is quite a bit more uncertainty at these highest discharges. And the sort of relationship between stage and discharge at those highest flows, you're getting the influence of roughness of bank vegetation, which is not what we're curious about. We're thinking about the river bed changing. And so the lower discharge measurements are actually more helpful to us. So for each one of these field measurements, we can calculate the stage residual by subtracting out the stage associated with that discharge according to the rating curve. So positive stage residuals in the past suggest that the stage was higher for a given discharge at that point in time than it would be now, and converse for the negative stage residuals. Okay, so these changes in stage residual are a proxy for channel change, but we ought to be a little cautious about how we interpret them. So we're going to go through a couple of checks here. Okay, so the first is thinking about width and roughness. So here I'm showing you for 3 different rivers, the time series of stage residual and the time series of a flow depth residual. So changes in the flow depth for a given discharge result from changes in width and roughness. So if we have flow depth residuals that are sort of like systematically changing with stage residual, then in our stage residual, we're probably seeing a messy combination of width changes, roughness changes, and aggradation incision. But what we see in almost all of these sites is that at all times, there is certainly variation in the flow depth residual. There are plenty of wiggles here, but they are not systematic with the changes in the stage residual, which is to say that, yes, it does seem that the width and the roughness vary a little bit. And this also might be sort of subtleties of the channel geometry of the bed that are shifting at the lowest flows or sort of in the Thalweg. But it's clear that there are sort of aggradation and incision signals here that outweigh. So this gives us confidence that when I talk about stage residuals, that I'm predominantly seeing bed elevation changes. The second check that we ought to do is thinking about sort of site-specific effects. So it is possible that the stage residuals that we're looking at could be reflecting very localized reach-specific characteristics, rather than giving us a broader understanding of river channel change in general. And the way that I went about thinking about this was that, you know, within a sort of geographic region, within rivers that are subject to the same climate, the upstream basins have similar hypsometries, the lithologies are similar, the processes are similar. We might expect this patterns of change to be at least somewhat similar. And so I've clustered these gauge sites, these are on the eastern flank of the Cascades. These are down in the South Cascades, sort of draining an area near Mount Adams. These are in the Central Cascades, draining to the west. And some of these are sort of upstream and downstream sites, and some of them are, you know, tributaries right next to one another. And what I see is that the character of the channel change, there does seem to be consistency within a basin. And this helps to give me confidence that what we're seeing here is not single bed forms migrating through a gauge site, but rather something about the environmental drivers. Okay, so here I'm showing you the time series of stage residual for all 49 of those sites. And we're stacking from the least variable through to the most variable. And I've scaled all of them vertically so that this height is the mean annual flow depth for each one of these sites. This allows us to more fairly compare between much larger rivers and smaller ones. So the first observation here, you know, most of these channels are remarkably stable, changing in their bed elevation by less than half the mean annual flow depth over a course of decades. And then, of course, there are a few that are quite unstable. Okay, so with these data, we can begin to ask what drives these patterns in channel variability. So as inspiration for this question, I want to take a look at a simple numerical experiment by Chenge An, who's one of Gary Parker's recent students. And this is what I'll show you in a moment is a 1D numerical model where at the upstream end, they are subjecting it to constant sediment supply and a cycled hydrograph. And then about halfway down their sort of numerical river, they're inserting repeated sediment pulses. And what they see is that through time, in response to both the cycled hydrograph and the repeated pulses, you see sort of variations in the channel bed elevation. I think this is sort of intuitive, but this is a nice framework to think about. So, you know, presumably the magnitude of the signal and the timing between perturbations, so the magnitude of the variation in flow and the magnitude of the sediment pulses and the timing between the high flows and low flows and between pulses shape the length scale of downstream response for each one of these perturbations. But this is to say that if sediment supply and hydrology are fluctuating through time but out of sync, we would expect to get variations. Okay, so with that sort of framework in mind, I'm going to consider two different flavors of drivers of channel bed variability. First, sediment supply fluctuations, and the second, peak flow events. So in this area, the potential sediment supply drivers of channel bed elevation change might be something about distributed landslides. So we have some of these basins are much steeper than others. And some of them have these large packages of quaternary sediment, either those last glacial maximum sediments, or in some areas, you know, we're talking about large packages of volcanic sediments. And another possibility is that we have proglacial debris flows that are driving channel change. So perhaps we could look at something like the percent upstream glacier area, the sites that have more than just tiny alpine cirque glaciers. And maybe that's what's driving change. And then in the category of peak flow events, well, these regional multi-decadal trends in climate seem to potentially matter for channel change. And so, you know, it's possible that we see those reflected synchronously in the region. A second possibility is that these channels might be greater in size sort of systematically in response to the individual peak flows. So we have these regional synoptic storms. We have some years where we'll have an atmospheric river come in and see landsliding all over the place. It makes the news. Do we consistently see, for example, aggradation in channels in response to the highest flows? Okay, so here I'm exploring correlations between channel variability and basin characteristics. So a simple sort of approach. On the vertical axis of all of these plots is the standard deviation of the normalized stage residual. So normalized stage residual being, these are in units of fraction of the mean annual flow depth for each river. And each dot represents one of our 49 sites. So I want to draw your attention in particular to these two plots. We find that the abundance of quaternary sediments in the upstream basin is not nicely correlated with the standard deviation in the normalized stage residual. So that certainly does not pan out. And somewhat surprisingly, neither does how steep the basins are. So this is the fraction of the upstream basin that is greater than 30 degrees slope. And we see that some of the most variable sites are, you know, the most shallow slope, and it's just a sort of shotgun blast. So these sorts of distributed sediment sources don't seem to explain the channel variability in this region. Okay, but of course, these small distributed landslides do cause channel change. So this is the North Fork Skokomish. This is upstream of the dam for those of you who were keeping track. And I think this is a really nice example of these small landslides causing channel change. So there's a remark in the gauge site notes that there was a landslide on the left bank about 610 feet above the footbridge that occurred in water year 2008. And this is water year 2008. And we see that bump in a stage residual. And so this is to say that sometimes your gauge is right within that downstream response zone of the sediment supply perturbation. But that for these sort of small landslides, that zone is probably pretty small. And so we probably rarely actually see the effects in the gauges. So let's consider now that possibility of proglacial debris flows. So here we're going to look at the unglaciated and glaciated basins. So this is, we're calling something glaciated if it has more than 0.5% of the upstream basin area covered in modern glacier. And here we have the standard deviation of the normalized stage residual. So we see that the rivers with large upstream glaciers have significantly more variable riverbed elevations than those without the glaciers. And I think this fits in really nicely with this pretty substantial body of work on the role of proglacial debris flows, these case studies from these channels, especially the ones on the flanks of the volcanoes or sort of in the crumbling Olympic mountains. Okay, so the sediment supply fluctuations, we see that, you know, the percent upstream glacier area really seems to be a significant driver of which channels are sort of bouncy in their elevations. But not all sediment supply is equal, and I feel the need to make this sort of caveat clear, right? So the downstream effects of sediment supply can be muted by abrasion. And this is likely especially important in this region, given that the glaciers seem to be a dominant driver and that many of our large glaciers are on volcanoes and stratovolcanoes. And tephra is extremely friable during bedload transport. And so this almost certainly complicates the fate of the sediment supply signals because the relative proportion of tephra and other non-vesicular volcanics will vary depending on the geochemistry of the volcano. So this is sort of a preview. If you're curious about that, make sure to be at CSDMS in May. We'll talk more. And the second thought here is that the starting size of the sediment is really important. I think we know this. So as an example in this data set, the South Fork Skokomish, which we talked about earlier, has coarse sediment contributed to the channel from paraglacial bluffs. This channel is one of the most dynamic rivers in the region. This is its stage residual time series here. In contrast, the North Fork Stillaguamish has fine sediment, paraglacial bluffs or glacial deposits. And this is a picture of the North Fork Stillaguamish. This was the site of the Oso landslide in March 2014, which caused 43 deaths and temporarily dammed the river. There was almost no response at this gauge, just a few kilometers downstream, because the sediment was silt and sand. And so this is sort of a reminder that, you know, both of these are quaternary glacial sediment deposits that on most of the maps that we would use to sort of guide our geomorphic interpretations, they're mapped as the same thing. And their sort of impact on the geomorphic response is substantially different. Okay, so let's turn now to considering peak flow events. So again, we could think about channel grading and incising in response to individual flows or thinking about multi-decadal trends. So we're going to take those individual peak flows first. So here we have the stage residual time series for the Nisqually River near National and its associated discharge time series. So here we see in between this field measurement and this time, there was a modest peak flow that resulted in incision. Okay, Fast forward a few years, there is, between this measurement and this measurement, there is a much higher peak flow event that results in a similar degree of incision. Then we have more than a decade of sort of marching aggradation at this site. And during this time, there is a much larger peak flow, similar to this one here, that is associated with a bed response that's just continued marching aggradation. Okay, so for each incremental change in stage residual from one time to another, we can calculate the maximum antecedent discharge, so the maximum discharge since the last field measurement. So here I'm showing you those data for 4 different rivers. We have our Nisqually River, Carbon, Hoh, and Duckabush. This one is not glaciated, but no volcano, and both of these are volcano glaciated. So on the horizontal axis, we have the maximum antecedent discharge associated with that field measurement. So each dot is a field measurement, normalized by the mean discharge for that site. On the vertical axis, we have that incremental change in the normalized stage residual, so a fraction of the mean annual flow depth. And increases are, so aggradation are in black and decreases are in red. So a couple of things that I want to point out. The first is that in response to the lower flows, we see little or less change in the channel bed elevation. This makes sense because channel change should be a threshold process, right? We need to exceed some flow to move sediment, let alone sort of reorganize the channel. And above some threshold, which for these rivers tends to be somewhere around 5 to 10 times the mean discharge, we see at times a greater degree of channel change. But it can be aggradation or incision, or sometimes in response to the largest peak flows, we see no channel change. In other words, high flows are necessary but not sufficient to cause aggradation or incision. And to emphasize here, when we see no channel change, this is not to say the bed is immobile. This is just to say that it's stable. So a mobile bed equilibrium, or perhaps there were aggradation and incision that happened and we just ended up at the same elevation. Okay, so now we'll look at all of the data. So what I'm doing here is we have the change in normalized stage residual, and we're looking at histograms. And so incision is to the left and aggradation is to the right. And these are the responses to the lower flows, the 5 to 10 times mean discharge and greater than 10 times mean discharge responses. So what we see is that flows less than 5 times the mean discharge tend to result in very little bed elevation change. Okay, makes sense, right? And a similar degree of change in the glaciated and unglaciated basins. The magnitude of the change in bed elevation tends to increase as flows increase. So those histograms are getting wider. The glaciated channels demonstrate a larger magnitude in bed elevation change. So the blue curves are wider than the black, and that there's a roughly symmetrical response. So we are about as likely to see aggradation as incision as a response to a peak flow event, with maybe a slight skew towards incision. But that the most common response, even to the highest flows, is no channel bed elevation change. So with that considered, let's turn to this question of multi-decadal trends. This is sort of thinking about that Nooksack data set and the connection to the Pacific decadal oscillation, which is a commonly referenced pattern of wet and dry periods. And I think before we think about channel change patterns through time, we need to establish the presence of these patterns in our peak flows at our gauge sites. So here we are looking at the fraction of our 49 sites that exceed 5 times the mean discharge and 10 times the mean discharge in any given year. So we have in this year, about 20% of the sites exceed 5 times the mean discharge, and no sites exceed 10 times the mean discharge. In this year, all sites exceeded 5 times mean, and 80% exceeded 10 times mean. So what we see in our data set matches our sort of regional understanding of the climate patterns experienced, that there was a much lower flow time period between the late 30s and mid 70s, followed by a time period of much higher peak flows. Okay, so there are some multi-decadal patterns in the peak flow events. Do we see this pan out in the gauge in the channel response? So here we're looking at the trend, aggradation, and incision, and the dashed lines are each of the 49 sites plotted here. And we have more data for the most recent 30 years or so than previously. And what we can see is that in these solid lines, these are the average channel trends, and they are quite near zero. And the sort of sites that do have trends, at any given point in time, there are sites that are grading and others that are incising. And in the most recent years, looking at just a couple of these sites, perhaps some of us might be tempted to say that there's more channel change happening now, but we don't have enough data to demonstrate that statistically. And so perhaps 20 years from now, we'll be able to look back and say that, regionally our channels are changing more now, but we can't say that yet. Okay. So I think this lack of regional synchrony and channel response makes sense in light of the fact that the glacial sediment sources seem to dominate. And that's because bed material waves take time to propagate down. And because our gauge sites are situated at sort of various distances downstream, and the sort of channel profiles vary, and the bed surface or the grain size of sediment pulses vary, we are going to, even if sediment signals were synchronous, we would see them at a variety of different times. And, the Nooksack is an example here, in the North Fork Toutle as well. Okay, so what drives patterns in channel variability? In the category of these peak flows, the individual peak flows, there is a threshold for the channel response to occur, but the response is not systematic. We don't consistently see aggradation or incision in this area. And, yes, there are multi-decadal trends in peak flows, but not in channel response. So the themes here. Most rivers in this region are remarkably stable, despite the fact that it's a really high sediment supply region, with many storms as opportunities to remake channel geometry. The rivers with upstream glaciers tend to be the most variable in the region, and there's a lack of regional synchrony and channel response. So here, channel response, does it primarily reflect sediment supply or hydrology? I would argue sediment supply. Okay, and so in the interest of time, I think I'll leave it at that with one quick other note, which is that, I think that this region probably responds differently than others. And that's because the volcanoes, our glaciers, are like creating an asynchrony between the sediment supply and the hydrologic forcing. And there are plenty of other regions across the world that probably are similar to this. But then if I went to California or over to the Appalachians, I might see a tighter coupling between hydrologic and sediment supply drivers. Okay, so with that, if we have time, I'll take a few questions.
Thank you so much, Allison. That was a really great talk. The chat is now open for questions. We also have the option to unmute yourself and ask the question directly. So me and Michal are going to take any questions you have. Oh, we already have one straight away. Okay, Alison will ask you them. So Paul Richardson says, what do you think is driving the long-term shift towards higher discharge? Land use, climate change? In Northern California, some of our biggest storms occurred in the 1950s and 1960s.
Yeah, that's a great question. So, hi, Paul. In this area, I think a big part of this, certainly in the higher elevation basins, is a shift from snow to rain. And so, you know, in 10 years ago, most of our atmospheric rivers, a lot of that precipitation would come as snow in the high elevations, and now it's increasingly coming as rain. And so our peak flows are increasing as a result, which is not the case for your Northern California 1964 blowout storm.
Awesome, thank you. I can go ahead and ask a question. Oh no, we have one already. I'll save mine.
Okay. I can ask it. All right, so this one is from Jess Zondervan, and he says, thank you for presenting loads of data. And you showed that thresholds are important to explain the patterns in aggradation and incision, but that these are not enough to explain river channel response. Either the channel would not respond, or either aggregate or incise after similar events. How could this be explained? Any ideas on the role of equilibrium states?
Yeah, so I think this has to do with sediment supply availability. So I think of this in that sort of, in like Chenge On's framework of the sediment pulses coming down partway down that sort of numerical channel, as you know, we might have a peak flow event in which the sediment supply is just what's in the riverbed sort of before the storm. And then there might be others where there was some landslide that happened that is now has a much greater supply of sediment for that given discharge than in the previous storm. So that's the framework in which I think about this sort of varying response to a similar hydrologic driver. And you know, equilibrium states. Well, I think that channels are very capable of reaching a lovely equilibrium channel bed elevation when they're subject to many little you know, distributed landslides, right? I think of that as like the background flutter of sediment supply to which these channels have adjusted. And it's when we have larger sediment supply pulses that are maybe more spaced out in time and happen at one place in the basin, so we can't have destructive interference of those signals downstream. I think that that's when we see aggradation signals.
Awesome, cool. Okay, so our next question is from Simon Mudd. He says, very thought-provoking, thanks. Given the hydrology doesn't appear to correlate with incision and deposition, what would we need to know to actually model incision and deposition in the future? Are our sediment transport models useless?
Oh, I hate that question. I mean, it's a great question. So I'm working with John Chuba and Katie Barnhart on a network-based morphodynamic model for channel bed aggradation and incision. And so I've thought about this a bunch, because basically where this work leaves me is saying we need to know what sediment supply is. We need to know when it's happening and the magnitude of it. And I think we might need to know the grain size distribution and something about the maybe even the abrasion potential in like coming off of volcanoes at least. And that's pretty hard. That's a pretty hard ask for a predictive modeling task, to say not just we need to get hydrology right, but we need to get the timing and magnitude of the sediment supply right. So I'm not going to say that our sediment transport models are useless, but I'm going to say that there might be some regions in which predictive modeling of bed elevation change from like predicting the sediment supply pulses on down is hard. Yeah.
For sure. Good answer. Michael, do you want to take the next one?
I can take the next one if you want.
Yes.
Yeah. The question by Mong Huang, who is writing, thank you for your talk. And in one of your background slides, you show a Google Earth satellite image. There seems to be a lot of deforestation in the Pacific Northwest. Would deforestation also influence sediment supply and channel mobility?
Yeah, so I've had some great conversations about just that, especially with Gordon Grant, who, for those of you who maybe don't know him, is a sort of hydrologist / geomorphologist down in Oregon, who has worked for many decades, especially on deforestation issues. And his view is that in all the data he's seen, we see big sediment pulses and big sediment signals post logging in the suspended sediment fraction, but that it seems to be much less, you seem to see much less of a consistent response to the bed material contributions after logging events. So that's one answer. And another is that, we started to try and grapple with this, but almost every single basin in our study area has been logged with different intensities at different times using different logging methods through time. So yeah, it's a good point.
Okay, great. Our next question is, how would sediment supply affect river evolution in tectonically stable tropical regions?
Yeah, that's a good question. And this is where, I think that what we found in this region, I think probably these wouldn't be the takeaways if we were looking to a more tectonically stable region or a tropical region. And then I think there would be much more tight coupling between the hydrology and sediment supply. So you might see sort of systematic responses to, the sort of modest peak flows, if I were to speculate, might cause incision, but the sort of blowout events might cause landslides and then cause aggradation. So you could imagine some potentially interesting patterns that could come out with a similar sort of study in a very different sort of geomorphic setting.
Future work.
So here's maybe another future work question. Aren't most of these gauge sites, it's from Paul Powers, sorry, aren't most of these gauge sites located in stable transport valley segments? Would you expect to see a similar signature if you looked at response or depositional valley types?
Yeah, that's a great question. And sort of an inherent limitation in this specific gauge analysis. These gauge sites, some of them are definitely in extremely stable valley segments, though the fact that, for example, when I did the sort of comparison within a basin, within the Snoqualmie River, some of our gauge sites were at, very confined, stable, laterally stable reaches, and others were less so. Yet the character of channel response was consistent across them, which makes me gives me a little bit of reassurance. But that said, yeah, I agree that we would probably learn really different things in looking at other sites, but you're just not going to get a long time series like this at those sites because the data don't exist. And that's where I think coupling sort of this approach with an air photo analysis, historical analysis, is probably the way to approach that consideration.
Cool. Pierre, you want to take the next one?
Okay, so there's a question by Tobias Hasser, who is writing wonderful talk. You look at the gauge residuals compared to peak flow discharge, so 5 times the mean discharge on higher threshold. What about looking at the number of 15-minute beans at partially mobile bed load or fully mobile bed load? Might that change the results, or do you expect it will not?
I did a little bit of exploring of this, and it seemed to not matter. And I think it was that it was that it would be that we would need 15-minute bins just above like some sediment transport threshold that's higher than the partial mobility threshold. So this is to say that I started going down that path. The results were actually much less clean. There were lots of the ones where there were many events in partial mobility, but zero change. And we would need to really do it right. We would need proper grain size distributions for every single site, which we don't have here. So I don't think it would change, but perhaps. It's a good thought.
Cool. I'm just going to back up. We missed one question. So how would your results translate to more engineered rivers and I can never say that word, anthropogenic changes in platform?
That is a fabulous question. And there's a PhD student at the University of Washington, Shelby Arndt, who's working with Alex Horner-Devine, who's actually gone and explored this a little bit. And it's actually pretty surprising that the modified rivers, and especially the ones downstream of dam sites, are extremely variable. And in this area, it's probably because we have all of these bluffs of sediment that are contributing into the channel in the lowlands. And so you can get sort of runaway aggregation happening when you decrease the peak flows. So folks are looking at this, and I think it has everything to do with the dam operations and the sort of details there.
Cool.
Yeah. Oh, we have so many questions. Just to make sure we are at so I didn't miss anything. We are at Chris Thomas's question, right?
Yeah.
All right. So he says, thank you for the great talk. And unless I missed something, is there any evidence for general gradual changes or trends in sediment supply in Northwest Washington, increase, decrease over the decades? Or is there evidence for local episodic increases in sediment supply in certain river channels as sediment sources become opportunistically available because of variation in the geology geomorphology?
I would tend to think that it's the latter, local episodic increases. That said, I don't know how I would measure sort of regionally an increase in sediment supply, especially because we have regional changes in hydrology going on at the same time. Yeah, I think, the retreat of these glaciers certainly points to a potential for higher sediment supply in those basins, and perhaps there will be more distributed landslides. But I don't think anyone has quantified that in a way that's really convincing regionally.
Cool.
Okay. There's another question by Simon Mudd, but I think you partially answered to that, but I pose it again. Well, did you ever look downstream of dams? Is there monotonic incision? So if you want to add something else, as you've already said about this.
Yeah, I might have expected monotonic incision, but it seems that at least in this area, there are some dams where downstream there are bluffs that are contributing. And so there's actually aggregation. But I think that's really site dependent and dam operation dependent. So.
True. Okay, next question. Thanks for a great talk, Allison. What about hysteresis? I mean, do you see greater or smaller changes just after large changes? Is there a change in the time between events?
That's a great question. I don't know that I've looked at that enough to say. Certainly, there are some sites that I can think of where it appears that the channel bed change, like if we think back to the Nisqually site, the channel bed change seems to be sort of independent of peak flows over the sort of multi-decadal time span. which I found somewhat surprising. And that was probably a huge pulse of sediment that's taking a long time to work its way through. So, there probably are history signals that we could pick out, but I think that would probably require a much sort of more careful look at a particular site. I think you'd need higher time resolution.
So our next question is, what is your opinion about the two significant bedrock canyon constrictions in the reach at and above the gauge on the Ho River regarding influence on your analysis of response to sediment supply, an inherent limitation?
Yeah. So there are, so maybe if folks have in these sort of systems where there are these constricted valleys, sort of inner gorges, and then broad response reaches or alluvial reaches between. And these are common in many of the mountains in this area. And yeah, I would say this is one of those sorts of inherent limitations. And I will again refer back to the consistency between gauge sites within a basin where we're looking at some sites that are in very constricted locations and others that aren't, and that the channel response character seems to be similar. To me, I guess that helps to reassure me that we're not just seeing sort of local effects, but it certainly is a limitation to this approach.
There's the next question by Rebecca Hodgie, which is writing, great talk, thanks. One other factor that might affect channel changes are the properties of the bed. For example, changes in the critical shear stress. Would this have an effect, or is it a minor impact compared to sediment supply on hydrology?
I don't think we know. The critical shield stress certainly is not a constant, and it certainly varies through time. But how much it varies, I don't think that we know. We have studies from flume experiments. We have a study from the Erlenbach, which, is at what, 17% slope, less than 1 square kilometer basin. I think that there's a lot of work yet to be done on that. So I don't know. I would guess that it is an effect, but I don't know how big.
Great. Okay, the next question. We have a lot of questions. You are treating peak flow as an independent input variable, but we know that channel morphology feeds back into the shape of the flood hydrograph. Do you have a feeling of how the flattening or steepening of your hydrographs change through time?
Ooh, I haven't looked at that. Yeah, I haven't thought about that. Certainly. I mean, the channel geometry, the width isn't changing much at these sites, but that's an interesting thing that I haven't thought about, but now I will. Thank you.
Cool. And Rebecca Hodge has just added, good to hear that grain scale research isn't completely irrelevant.
No, I have a master's student going out probably later this afternoon to go push on pebbles and ponder that exact question. So I'm totally on board.
Sounds like an ideal thing to do right now. Maybe some gravel.
It's a little cold right now, so would be nice, but.
So that's all the questions we have, unless there's any last minute ones that we might give Allison a break. I think that was a really great talk and a great session. Thank you so much again. And yeah, hopefully see everyone next week. I think there's no more questions. I don't want to cut anyone off, but yeah. Thank you very much, Allison. And thank you everyone for coming.
Thank you all. It's lovely to see your faces.
Awesome.
All right, thanks, folks. Thank you for the invitation and for moderating. It's wonderful what you all are pulling together, pulling all these people together. So thanks.
Thank you. And I think we had
Thank
a
you for the talk.
record number of participants. It was 162. You're famous.
That's better than a conference talk in a lot of conferences. Impressive.
Perk of quarantine, right?
Yeah. All right. Well, thank you all again, and I'll see you around.
Yeah. Thank you.
Thank you, Allison.
Bye.
Bye-bye.
Ciao.
Ciao.